Spectrum is a project that has been funded by the European Commission in the framework of the Horizon Europe EIC Transition Open program. The project started in May 2022 and ended in April 2025. The consortium behind the Spectrum project includes excellences in both the academic and industrial sectors. The two academic institutions, CNR Nano and University of Chalmers, led the scientific and R&D activities of the project, supported on the engineering by Intermodulation Products and Bilfinger, and by Day One for the exploitation of the project outcomes. The activities of the Spectrum project are carried out in the scope of the quantum computing field. Quantum computing leverages the principles of quantum mechanics to process information differently than classical computers. Unlike classical bits, the so-called quantum bits or qubits can exist in superposition and interact through entanglement, enabling massive parallel computations. The advantage of quantum computation is that it makes problems that are too complicated for the classical computation solvable in very short times. In fact, quantum computing promises to solve certain classes of mathematical problems using new algorithms capable of revolutionizing areas such as drug development, simulations of complex physical systems, but also more common problems such as air traffic management and cryptography. Unfortunately, the spread of quantum computers is limited by two major issues: high cost and low scalability. The cables carrying signals and power inside the cryogenic chamber. Each cable is in fact expensive, bulky, and disrupts the system's thermal stability due to the thermal load, which can affect performance and cause downtime. This, because quantum computers work at very low temperatures, close to absolute zero. The main objective of Spectrum is to transform the analog control of the quantum processing unit, or QPU. The QPU is the heart of the quantum computer, where individual qubits are kept stable and operated by extremely fine superconducting electronics. Today, each qubit and each logic gate is controlled via signal lines, mainly analog. Spectrum transforms the analog control of the QPU via time division signal multiplexing. This is possible thanks to QueSt. QueSt is an innovative switch based on a suitably engineered Josephson junctions transistor developed in CNR, which drastically reduces the number of lines necessary to control a QPU. If we focus on today's superconducting quantum processors, which have reached and exceeded 100 qubits, this means over 300 signal lines inside the cryostat. With QueSt, this number drops to less than 10 lines, most of which are control lines. This not only dramatically reduces space but also the design complexity and overall computer costs. The consortium developed and realized several prototypes based on the innovative Josephson field effect transistor based on INAS-OI. These prototypes are currently being tested within the quantum machine installed at Chalmers University of Technology, in Gothenburg, Sweden, to optimize its integrability and performance.